Hello again, everybody. This is our video solution to problem 14a from the Fall 2020 Math 210 final exam. In this problem, we're given a series for which we want to compute the radius and interval of convergence. Of course, this is going to require us to use some sort of series convergence test. And given the shape of this thing, right? First, it's a power series. Then we have all these exponents. This suggests one of two very reasonable approaches, the ratio test or the root test. My preference is typically the root test when I can use it. So that's what I'm going to use here. But you'll find the ratio test can be used quite readily here as well. So let's do the root test though. So for the root test, I'm going to be taking the limit as n goes to infinity of the square root. Well, it's not really a square root, right? It's an nth root. So I take an nth root, and then I need to take an absolute value, right, of my nth summand. So I take the absolute value of here, n to the 99th power over 5 to the n plus 1 to the 100th power times x plus 3 to the nth power. All right, now the nice thing is everything here is being multiplied together, and the absolute value as well as the nth root are going to coexist very nicely with multiplication. So I'm going to be able to rewrite this as this limit as n goes to infinity of, all right, so we're just going to break this up into little pieces. The nth root of, now let's see, do I need absolute values on anything? Well, the n, that's always going to be positive. Let's see, the 5 to the n, that's always going to be positive. N plus 1 to 100, that's positive. X plus 3 to the n, that could potentially be negative. X, right, that has free reign potentially of all real numbers. So that's the one place we're going to have to leave the absolute value. So let's see here. So here I can just write the nth root of n to the 99th power. I also get the nth root of x plus 3 to the n, and then we'll put some absolute values, which I can even put the absolute values inside the exponent. So let me do that so long as I'm here. So absolute value of x plus 3, and then we'll raise it to the n, divided by the nth root of 5 to the n, and the nth root of the 100th power of n plus 1. Okay, so let's look at these individually. Well, actually, kind of the two easy ones here are when I have the nth root of an nth power. Those are just going to go away. Okay, so this bit here is actually just equal to the absolute value of x plus 3. And the fifth root of 5 to the n, this is just going to equal 5. Okay, so actually, let me pull those out, because those have nothing to do with n. So I have the absolute value of x plus 3 over 5 times the limit as n goes to infinity of the nth root of n to the 99th power over the nth root of n plus 1 to the 100th power. And the n plus 1 to the 100th power is not much different from n to the 100th power, right? And both of these I can immediately evaluate their limits using, we have a nice little rule, which said if you had the nth root of n to the p is some positive value, that this converges to 1. Okay, so this means that the top converges to 1 and the bottom converges to 1. Yeah, again, I have an n plus 1, but that really doesn't change things as n grows. So actually, my limit is simply going to be the absolute value of x plus 3 divided by 5. Okay, well, what does that tell us? Well, we have to go back and say, what the heck were we doing, right? Well, we were using the root test. And the root test tells you get a convergent series if this limit we computed is less than 1. And you get a divergent series if the limit is greater than 1. So let's determine when this is less than 1. So the absolute value of x plus 3 over 5 is less than 1 if and only if the absolute value of x plus 3 is less than 5. So I just multiplied both sides by 5. Well, I can draw a nice picture to easily see what's going on here, because what does this mean? When I have x plus 3, I could really think of this as being x minus negative 3. And the absolute value of a difference is telling you the distance between. So this is saying the distance between x and negative 3 is less than 5. So let's put negative 3 here in the middle, and we want all the x's that are within 5 of negative 3. Well, if I go to the right 5 distance, that would take me to 2. If I went to the left 5 distance, that would take me to -8. Therefore, I know I get a convergent series between -8 and 2. Okay, so I mean, and I can immediately now say that my radius of convergence is 5. Okay, so the radius of convergence is going to be 5. Now, we also know that you're going to diverge once you get outside of -8 and 2. The only thing left, and this is where people tend to forget that they need to do this, especially this part of the semester, is we need to check the endpoints. Why? Well, at -8 and at 2, that's where we would have gotten that this ratio, absolute value of x plus 3 over 5, was equal to 1. And the root test doesn't tell us anything about what happens when that ratio is equal to 1. So we need to check those individually. So those two cases we know specifically are when x is -8 and x is 2. All right, so let's look at what happens to our series when x is equal to -8 and when x is equal to 2. All right, so when x is equal to -8, our series becomes, let's see, so we're starting it at 0. We have n to the 99th power over 5 to the n plus 1 to the 100th. And then the x plus 3 becomes -8 plus 3 to the n. And of course, this is becoming what? -8 plus 3 is -5 to the nth power. And of course, I could rewrite this as an alternator times 5 to the n. Okay, this 5 to the n that we get is going to cancel with the 5 to the n we have down here. So we're left with this series, n to the 99th power. We have an alternator over n plus 1 to the 100th power. Hey, that's actually not terrible. It's also not immediately obvious what we're supposed to do with this thing. But, okay, it does have an alternator. And when we see an alternator, maybe an alternating series test isn't terrible. So to use the alternating series test, we need two things to happen, right? If we get rid of the alternator and just look at the underlying series, so n, or sequence, n to the 99 over n plus 1 to the 100th, we need this to be eventually decreasing. And we also need that it converges to 0. Okay, I'm not super worried about the second part, right? Let me show you why. I'd like to raise these both to the same power. So what I could do is, for example, pull out one of these n plus 1s in the bottom so that I have n over n plus 1 to the 99th, and then I need one more n plus 1. That would give me my 100th power in the bottom. Now, n over n plus 1, as n grows to infinity, this is converging to 1. But 1 over n plus 1, that's converging to 0. And so in total, this product, right, is going to converge to 0. If you like, another way to see it is this n over n plus 1 to the 99, that's always less than 1. So this product is less than 1 over n plus 1. Of course, this entire product is greater than 0. But 1 over n plus 1 converges to 0. And so by the squeeze theorem, right, our underlying sequence is going to converge to 0. So this one checks out. I am a little bit more worried about this eventually decreasing. It definitely feels like it has to go to 0, and so it has to be getting smaller. But how do I know that it's just constantly decreasing as I go? So one way that I can see this is by writing down a generating function and taking a derivative. So if I look at x to the 99th power over x plus 1 to the 100th power, and I take a derivative. If I can get this to be negative for some x and above, then I'll know I have a decreasing sequence. So I use the quotient rule here. So let's see, low, d high. So let's see, that's going to be 99 x to the 98th times x plus 1 to the 100th. less high d low, so we'll get 100 x plus 1 to the 99th times x to the 99th over x plus 1 to the 100th squared, that'll be the 200th power. So this is going to be less than 0, which would mean my function is decreasing, if and only if, well, the denominator is always positive because I have an even power. So I'm going to know that this fraction is negative if and only if the numerator is negative. And so if this is negative, well, I could just add this 100 blah, blah, blah to the right, and I'll get that 99x to the 98th times x plus 1 to the 100th has to be less than 100 times x plus 1 to the 99th times x to the 99th. All right, well, I'd like to do some division, which I'm going to be able to do because since I'm going to infinity here, right? N's supposed to be going to infinity. I may as well assume x is positive. So let's see here. I could divide by 100. I get 99 over 100. I could divide by x plus 1 to the 99th. And that's going to get rid of all of these except for 1. So I'll have an x plus 1. I could divide by x to the 98th. And that'll just give me 1x on the right. Let's see here. Now I can distribute this. This is 99 over 100x plus 99 over 100. I can now subtract 99 over 100x from both sides. And I'll be left with 99 over 100 is less than 1 over 100x. All right, let's clear denominators, multiply through by 100, and I get that 99 is less than x. Whew, when we said eventually, we really meant eventually. So this is telling us that the derivative of the generating function is negative if and only if x is greater than 99. So that's where eventually starts. All right, when I get past 99, then this function is actually, we know, a decreasing function. All right, so this justifies saying that we have a sequence converging to 0, which is eventually decreasing. And therefore, we can apply the alternating series test. And the alternating series test is great because it says, if you know that your underlying sequence, right, without the alternator is eventually decreasing and converges to 0, then automatically 100% your series converges. Beautiful. All right, so that means we can go back up a bit, and we know that we're going to get -8 in our interval of convergence. So we get to include -8, and now the only issue is, will we or won't we get to include 2? All right, well, let's check it when x is equal to 2. So the only difference is going to be I'm going to have a 2 plus 3 to the n instead of a -2 plus 3 to the n. And so, okay, well, we can copy this down, but we're kind of wasting time by doing so. We know what's going to happen here. N plus 1 to the 100th, but now we're going to get 2 plus 3 to the n. So we get the exact same thing out, except there's no alternator, because this is now 5 to the n instead of -5 to the n. So my series becomes, we can do a little better, greater than or equal to sign there. My series becomes n to the 99th over n plus 1 to the 100th power. And I should be a lot more skeptical about this thing converging because that alternator isn't there, and because this denominator, right, what's that first term going to look like? Well, let's break this up a little bit. I have n to the 99 over, when I distribute, I'm going to get n to the 100th power plus, well, now everything else is going to be powers of n that are no bigger than 99. So remember, we could write this as O of n to the 99th power. You could just, again, we didn't talk explicitly about the meaning of this notation other than to say, right, everything has power 99 or less, right? And the important thing is, if we're trying to find out what this fraction, this sequence generic term is going to be asymptotically equivalent to, we only care about the highest degree terms, right? So n to the 99 over n to the 100, that's just basically going to be 1 over n. And we know that if you do the series for 1 over n, that's the harmonic series. It's going to diverge. So we should predict that this thing this series is going to diverge. Now, we can prove this formally. In fact, let's do that. Okay, so we want to now use the limit comparison test. So what I'm going to do is I claim that n to the 99 over n plus 1 to the 100th is asymptotically equivalent, right, as a sequence to the sequence 1 over n. Okay, so to show that this claim is true, I need that, of course, all these are eventually positive. Of course, they're always positive. And I need to look at the ratio of their nth terms. So I take the limit as n goes to infinity of the nth term here. Okay, that'll be n to the 99th over n plus 1 to the 100th. And I'm going to divide by 1 over n, which is the same thing as multiplying by n over 1. All right, well, this is pretty easy to combine now. And I put the n's together. I have n to the 100th over n plus 1 to the 100th. And now I can kind of factor out this 100th power. I get n over n plus 1 to the 100th. And again, we know that n over n plus 1 converges to 1. And so this 1 to the 100th is also going to converge to 1. Okay, but 1 is positive, and this tells you that these two sequences are asymptotically equivalent. All right, since these are asymptotically equivalent, this implies that the original series, n to the 99th over n plus 1 to the 100th, converges if and only if the series, well, okay, now there's this little issue when we try to evaluate n at 0. So why don't we just start it at 1? Okay, we can start it at 1, and we know that that's not going to change whether or not our series converges or diverges. So we'll put an n greater than or equal to 1 here, and then we have a 1 over n. But we know that this is the harmonic series, and it diverges. And so that tells us that our series diverges. So this implies that the series starting from 1, or even 0, n to the 99th over n plus 1 to the 100th diverges. So in the x equals 2 situation, we get a divergent series. So we're not going to include 2, and so our interval of convergence is -8 to 2.